Okay, so continuing on with chapter 9, let's talk a little bit more about selective transmission. All right, so selective transmission is once again where an object acts as a filter. It absorbs certain wavelengths of light and allows others to pass through. And a good example of this is a liquid, right? You might have a liquid that is like, for example, if you have a bottle of Big Red, right? The Big Red soft drink, and you look at it, it looks red, and because the colors, the liquid inside that bottle is absorbing all the other light that passes through it except for red. That the red color is passing through and ultimately making it to your eye so that you perceive that bottle of Big Red as red. The other thing about color is that we perceive colors not only based on what the actual wavelengths that are bouncing off of that object are, but one of the other factors that influences how we perceive color is in fact the colors that are next to it. So in other words, if a color is sitting on a background of another color, so let's say you have a red sitting on a red block or a red square sitting on a black background, that red is going to look different to you than if it was sitting on a white background. If that red is sitting on a white background, it's going to look more washed out to you, not as brilliant to you as a red square that would be sitting on a black background. So our perception of color is affected also by the objects that color is sitting next to. There's a lot of different ways that we make colors, of course, right? One of the general methods for creating different colors is by additive process, an additive color mixture. And this is what happens when we mix different lights of different wavelengths. So if you have a light, for example, that is blue and another light that's yellow, and you shine them together in the same spot so that they're superimposed on each other, it's going to look white. If you have say a red light and a blue light, shine them together, it's going to look kind of purplish, right? So this is a way of producing different lights by adding different wavelengths together, and most commonly seen with lights. Bouncing lights off of objects and mixing different colors of lights together, which is of course something we do with advertising and TV production. That's and stage productions, right? There's different colors of lights that are used to achieve different colors and different effects. Similarly, with paints and things like paint and Play-Doh and things like that. The process of changing the colors of those things is through subtractive color mixing. So, for example, if you want to make the color purple, right? You want to make the color purple with paint or with some Play-Doh, you're going to mix blue and red together. You're going to get some blue pigment and some red pigment, mix them together and create the color purple. What's going to happen is that fewer wavelengths are going to be reflected off of that object. So let's take the example of green. If you mix blue and yellow together, it's going to make green. The only blue and yellow are going to bounce off of that object. Nothing else will bounce off of that object and will give you the perception of green. So once again, with a physical stuff like paints and pigments and clay and Play-Doh and crayons and things like that, you create colors ultimately by this subtractive process. That when you mix the pigments together, it's going to reduce the number or subtract out the number of wavelengths that are bouncing off of that object. But with lights, what you're doing is you're adding wavelengths together. You're adding this wavelength and this wavelength to make a combination of these wavelengths or of this color. So here's an example of the light, right? So, mix blue and yellow and you end up with green. So the short wavelengths mix with the medium and long wavelengths, and you end up. You make white. This is how you make white light. You get the blue wavelengths and the yellow wavelengths. They mix together. So the short wavelengths are in the blue, and then yellow is made up of medium plus long wavelengths. And as you know, short plus medium plus long wavelengths gives you white. So that's how we get white light on a stage setting, for example. And once again, we have these pigments, which looks like poop, but this picture, right? But we have these pigments here, right? For example, we have some blue pigment, right? So notice that the blue pigment, right? What's happening is that different wavelengths are hitting the blue pigment, right? And in this blue pigment, what's happening is that the red is getting completely absorbed. And you have some blue, a lot of blue and some green bouncing out of there, right? But the red is getting completely absorbed. And then in the yellow pigment, you have the blue getting completely absorbed, but medium and long wavelengths being reflected off of there. Well, when you mix them together, you get this subtractive effect, right? Where the short wavelength is canceled out by the long wavelength, and vice versa. So they're canceled out, and the only one that you have left is the green wavelength. So you've subtracted out by mixing the pigments, by mixing blue and yellow paint or blue and yellow clay or Play-Doh. By mixing the blue and yellow pigments together, you end up canceling out certain wavelengths and only allowing another wavelength to not get absorbed and bounce off of the object and ultimately end up in somebody's eye. So here's a nice handy little chart. It's table 9-2 on page 203 of your textbook. And let's see. Oh, there it is. Oh, no, wait a minute. Where is it? Oh, there it is, yeah. So it's on page 203 of your textbook, table 9-2. And 9.2, I should say. And so what this does, right, this gives you a summary of what happens with additive color mixing when you're mixing blue and yellow lights together, right? So if we look at a spot of blue light, if we're looking at a spot of pure blue light, right, what we see is short wavelengths being reflected, no medium wavelengths being reflected, and no long wavelengths being reflected, right? So since only the short wavelengths are being reflected, all we see is blue. With a spot of yellow light, we have no short wavelengths being reflected. We have some medium waves being reflected and some long wavelengths being reflected. So since we have medium and long wavelengths reflected, but no short, we perceive that as yellow. Well, since this is additive, since it's lights, we add these colors together, right? We add these wavelengths together. So we end up with blue being reflected, the medium being short being reflected, I should say, which we perceive as blue, medium being reflected, which we perceive as green, long being reflected which we normally perceive as red. And when you reflect all three of those together, combined, the blue, the green, and the red combine to have us perceive white light. So here we have an example of mixing paints to do subtractive color mixing. So in this example here, we have a blob of blue paint, a blob of yellow paint, and the mixture of the two blobs together. So let's look at the blob of blue paint, right? The blue paint looks blue to us because it reflects all of the short wavelengths. So the molecules in that blue paint are constructed in such a way so that they do not absorb any blue, but it all reflects off, right? So it gets reflected off. Medium wavelengths in the blue paint, some of them are reflected, very few, but some are. And then finally, all of the long wavelength light that hits that blob of blue paint is reflected, meaning that all of the red is absorbed by that blue paint. So since mostly short is coming off of it, since mostly short wavelength is coming off of that blob of blue paint, it means that it's going to look blue to you. Similarly with the yellow paint, the short wavelengths are all absorbed, so all the blue's getting sucked up. It reflects some of the medium and it reflects some of the long. So since it reflects some of the medium and some of the long, a little bit of each, those two combine to those two colors that are reflected off of that object combine to give you the perception of yellow. Well, when you mix them together, right? When you mix them together, you end up with this substance, the mixture blue and yellow, where you've got the absorption, right? So since you've got the absorption of all of the short wavelengths, right? Because yellow does that. You've got the absorption of all of the blue wavelengths because blue does that, right? So you've got all that absorption going on. But in the medium, right? In the medium, you've got some reflecting in the medium wavelengths. Of course, medium wavelengths are perceived as green by our eyes. So since that's all that's bouncing off of that object is medium wavelengths, because everything else is being absorbed by the molecules in that paint, we perceive it as green.